Welcome to This Explainer. Today, we are literally peeling back the layers of your computer's software ecosystem. From those everyday apps you're constantly tapping on, all the way down to the raw machine code that, well, actually makes the hardware tick. So if you've ever wondered how all these incredibly complex moving parts communicate seamlessly without everything just crashing, you are definitely in the right place.
Okay, let's take a quick look at our roadmap for today. We're going to break things down into 5 key areas. First, categorizing software. Then, utility software. Third, the operating system. Fourth, interrupts. And finally, programming languages. Let's dive right in.
Section 1. Categorizing software, the surface layer.
So, the best way to think about your computer is kind of like a massive theater production. On one side, you have system software. This is the stage and the stagehands. It controls the hardware operations and basically provides that vital platform for absolutely everything else to run on. On the flip side, we have application software. These are the actors on the stage. They're the specific, highly focused programs you run to actually get your everyday tasks done. To put that into perspective, whether you're firing up a word processor to type an essay, using a spreadsheet to crunch some serious numbers and run those what-if calculations, or pulling information from a database, you are using application software. It even includes those highly specialized tools you use for photo, video, and graphics manipulation. Tweaking colors, adding digital media transitions, the whole shebang. These are your purpose-built tools, designed specifically for your end goals.
All right, moving on to Section 2, utility software, the maintenance crew.
Right beneath those everyday apps is a crew of absolute unsung heroes. By definition, utility programs are specialized pieces of software that manage, maintain, and control computer resources completely in the background. They keep your entire system optimized and secure, and the best part? They do it without needing constant input from you.
Take disk defragmentation, for example. When your hard drive starts feeling super sluggish? Well, as you delete or extend files over time, new data doesn't perfectly fill those vacant gaps. The data blocks just scatter all over the disk surface. This forces the physical read-write head to frantically jump around to piece it all together, which, as you can guess, slows everything way down. Defragmentation swoops in, rearranges those scattered blocks back into nice, contiguous, neighboring sectors, and drastically speeds up your access times. It's a real game changer for older drives.
But beyond defragmenting, your system relies on a whole suite of these background tools. You've got virus checkers running heuristic checks, meaning they can identify unknown malware based on suspicious behavior, even if the virus isn't in their database yet. Pretty smart, right? Then there's backup software keeping your data safe, security software managing firewalls and encryption, and device drivers. Think of drivers as essential translators. They convert system data into a format that your newly plugged-in printer or USB device can actually understand.
Which brings us to Section 3, the operating system, the master controller.
So the operating system, or OS, does an unbelievable amount of heavy lifting. It's essentially the ultimate multitasker, seamlessly establishing communication between you and the hardware. Behind the scenes, it's constantly managing memory allocation, opening and deleting files, handling errors, and carefully sharing hardware resources across different processes. This is what lets you multitask so smoothly, all while providing absolutely crucial security features like user accounts.
But here is a cool question. How does a computer actually wake up and start this massive operating system in the first place? When you hit that power button, the raw hardware literally doesn't know what an OS is. It first looks to the firmware, specifically the BIOS, or Basic Input-Output System. Inside the BIOS is a tiny, incredibly important program called a bootstrap loader. It tells the computer exactly where to find the operating system on your storage drive so it can boot up and take the wheel.
Now, once it's up and running, the OS has to give you a way to interact with it, an interface. We essentially have 2 main flavors here. A command line interface, or CLI, gives you direct, highly efficient, low-memory communication. The catch? The learning curve is steep because you have to type exact commands flawlessly. On the other hand, we have the Graphical User Interface, or GUI. This uses those intuitive visual windows, icons, menus, and pointers. It is incredibly user-friendly, but the trade-off is that it eats up a lot more system memory just to render all those pretty graphics on your screen.
Okay, moving to Section 4, interrupts, handling the unexpected.
Let's think about this for a second. Imagine you're printing a massive document while simultaneously downloading a huge file, and suddenly, the printer jams, or maybe an application completely freezes up. How does the computer know to immediately stop what it's doing, alert you, and fix the emergency without the entire system just crashing to a grinding halt? Well, the answer is an interrupt. It's exactly what it sounds like. It's a priority signal sent from a device or software directly to the microprocessor. It essentially yells, "Hey, stop what you're doing right now, this is a top priority." It forces the processor to pause its current ongoing tasks so it can temporarily handle this urgent event. So when the processor sends data to a peripheral, say outputting that document to your printer, it pushes that data stream through a temporary memory buffer. If the printer runs out of paper, it fires an interrupt signal right back to the microprocessor. The processor instantly hits pause, services the interrupt, usually by popping up a warning on your screen, and once you clear that paper jam, the data stream resumes right from the buffer exactly where it left off.
And honestly, these interruptions are happening constantly. We're talking millions of times a second. They can be triggered by scheduled timing signals, basic input/output requests from your disk drive, hardware faults like that paper jam, or even just you pressing a single key on your keyboard. Oh, and they are also triggered by software errors. For example, if a program suddenly tries to locate a missing executable file or attempts an impossible math equation, like trying to divide by 0, bam, that's an interrupt.
Finally, let's look at Section 5, Programming Languages, Speaking to the Machine.
You might be wondering, how is all this incredible software actually built? Well, we categorize programming languages into two distinct levels. High-level languages are much closer to human language. They're independent of specific computer hardware, making them way easier for developers to read, write, and debug. On the flip side, we have low-level languages like assembly or raw machine code. This is what the computer hardware actually understands natively. They run insanely fast and take up almost zero space, but man, they are incredibly difficult and time-consuming for humans to write.
Because our computers only read that low-level machine code, we have to use translators to bridge the gap between human and machine. A compiler translates an entire high-level program all at once, producing a standalone executable file that can run on its own. An interpreter, however, executes a high-level program one single statement at a time without creating an executable, which is super handy for real-time testing and debugging. And then we have the assembler, which is specifically built to translate low-level assembly language directly into machine code.
To write and translate all this code efficiently, developers rely on Integrated Development Environments, or IDEs. Think of an IDE as the ultimate digital workshop. It bundles all the essential tools a programmer needs into one convenient software package. You get your text editor, the translators we just talked about, debuggers, error reports, and incredibly helpful quality-of-life features like auto-completion and code formatting. It really is the whole package.
As we wrap up this explainer, I want to leave you with a fascinating little paradox to chew on. An integrated development environment is technically a piece of high-level application software, right? But developers use it to write the very system software and operating systems that allow application software to run in the first place. So, if applications build the systems and systems run the applications, which layer of the ecosystem is truly in charge? It's a pretty brilliant loop of dependency that makes all of modern computing possible. Thanks for joining me today, and I really hope you leave this with a much clearer picture of the incredible ecosystem operating just beneath your screen.